want to talk to you about looking inward as well, and as well as looking outward, and how it's changed how that's changed over the last 50 to 75 years. And it's an amazing story. It's a remarkable story that's not really appreciated. And I want to start you off to give you a sense. So anyway, I'll forget that quote. But I do want to point out that the story of the rise of what I call the standard model of particle physics is much better than any man-made myth. And as you'll see, it's a sublime mixture of culture and technology. And it also suggests, once again, that not only are you insignificant, which you are, I hope we got that out of yesterday, but that, in fact, we are just a cosmic accident, and it could have been quite different. So, okay. So I want to start with The Lion, the Witch, and the Wardrobe. How many people have ever read that? Well, look at that. See, it's everyone like... It's kind of a con job. It's really a religious story, but it's nevertheless a fun kid's story. But you may remember that when the kids get shipped off to the professor's house in the country, they find this wardrobe, which is how they get to Narnia. And it's an amazingly interesting thing if you think about the physics of it, because you can go behind the wardrobe, it's just there, but then when you go in the wardrobe, you've got to go get a whole new universe, literally a whole new universe. And what I want to point out to you is it's actually conceivable that that's the situation we're about to be in terms of the experiments we do with small scales. And you'll see, so we are potentially about to open a wardrobe that is similar. And I want to start, though, way back. I want to take, this is a story that's over all of human history. So I want to start back with this guy here. Does anyone know who this guy is? Is he classically trained? Not Aristotle. It's not Socrates. You're getting close. The other one. Plato. That's right, Plato. Plato, I mean, they were all, classical philosophers and better or worse in some ways than others. But Plato was quite interesting to me when I was a little bit younger than you. Well, no, but yeah, a little bit younger in high school, because I was forced to read Plato in high school. And I remember Plato's Republic, and there's a great story in there. It's a parable of the cave, and it had a lot of impact on me. And it's interesting. You'll see it's kind of relevant. So Plato imagined that really, when we're looking at reality, we're like people in a cave that are just looking at shadows of reality. And so this is from my high school textbook, probably from the 1950s. So he imagined that humanity was kind of like tied and shackled to look at only the shadows of reality, only to see the shadows on a wall. And the job of the philosopher, he said, or the mathematician, was to somehow interpret the shadows and understand the underlying reality underneath. And that's quite poignant, as you'll see. This is also timely, because it's interesting to see that in the 1950s that the people being shackled involved having sort of scantily clad women in chains, which would be inappropriate now, I think, but and should be inappropriate. But let us think about what it would be like if you were such a philosopher or a mathematician in such a world, if you could only see the two-dimensional shadows of a three-dimensional reality. Let's say, for example, if you were living in such a world, you would say there's no such thing as length. Because length is not constant. Objects change their length all the time. You could see the shadow of a ruler on the wall at one moment, and then a little bit later see the shadow of the same ruler, and it would have changed its length. So you would say there's no such thing as length. And that's if you were just the common person. But if you were the philosopher or mathematician, you'd think about this and say, no, I understand what the situation is. What really, the world isn't two-dimensional. The world is three-dimensional. Here, let's see if I can do this. No, I don't think I can do it very well, but with the lights, maybe. So here, can you see my shadow of my arm there, right? So that's the shadow of my arm. But of course, if I rotate my arm, the shadow of my arm gets smaller. I'll just show you the picture. So let's say there's a ruler, and the light is coming from behind, and the ruler's there, and I get the shadow. And if I were to rotate the ruler in another dimension, which the mathematician could imagine actually existed, even though you couldn't see it, then he'd say, really, what we're seeing is, of course, the projection cosine or sine of that length if you want to think about it. So we're seeing the projection on the x-axis of the ruler, and so in the real world there really is something that you can call length that is constant and unchanging. But our perception of it is just the fact that we are only seeing literally the shadow of reality. Okay, so that's the kind of thing the mathematician, philosopher would have to do at that time. And by the way, Plato said that if you really were a mathematician, and if the philosopher was ever taken to the outside world and actually shown it, and then came back to try and talk to people about what was actually happening, he'd be basically put in a lunatic asylum because no one would believe it or listen or understand. And sometimes I feel that way myself when I talk about some of this stuff to the public. I did last night. I felt that way when I was on a TV program. Anyway, okay, so that's we're jumping. I'm going to go all the way from Plato and that, and I want you to keep that in the back of your mind, okay? Because that concept will become important to us later. To this guy, who's this guy? Anyone know? Michael Faraday, the greatest experimental physicist of the 19th century, another hero of mine. He's responsible for basically everything in this room. Electromagnetism as a tool to operate everything we see, and all the tools and all the motors and basically everything that runs modern civilization. There's two things I should tell you about. One is very important to you, which a valuable lesson learned from Michael Faraday is to always suck up to your professors, because he started life. He had no formal education. His family was poor, and I think he stopped school at age 10 or 11 and was apprenticed to a bookbinder. He was apprenticed for about 7 years, and he attended the lectures of Humphrey Davy, who was the head of the Royal Institution in London, a famous chemist. You may have heard of his name. And he attended those lectures, and he took beautiful notes. And then he bound them in a book, and he presented them to Humphrey Davy. He said, "Here are your lectures in a book. Can I be your assistant?" And Humphrey Davy said yes. And in fact, Faraday moved up to eventually become the director of the Royal Institution, and as I say, the most famous and best experimental physicist of the 19th century. He also was doing all these experiments on electricity and magnetism, and it was rather esoteric. There's very many apocryphal stories. None of them are probably true, but it's said that the Prime Minister of England came into his laboratory and looked at all this useless stuff and said, "Of what use, is any of this stuff that you're doing?" And Faraday said, "It's so useful that one day you'll tax us for it." And he was absolutely right, because every time you plug things in the wall and use electricity, you get taxed now. But at the time, it was a new world, trying to understand the nature of electricity and relate something that, in fact, was sort of clear but not so clear. You've all, undoubtedly, because of your interest in physics, played with magnets when you were a kid. Okay? Magnets. And you've all played with static electricity. Okay? And hung balloons on a wall and all the rest. It became clear by the time of Faraday that there was a relationship between electricity and magnetism. If, for example, you took a charge and moved it, as you produce a current and therefore a magnetic field around the current. Okay? That was known. So a moving charge produced a magnetic field, and therefore it produced a force on another magnet. So that was known, and therefore people tried for the longest time to say, well, if a moving charge can produce a force on a magnet, can a magnet produce a force on a moving charge? In fact, a magnet could produce a force on a moving charge, sorry. Could a magnet produce a force on a static charge? Could a magnet somehow produce an electric force? Because a moving charge produces a magnetic force. Could somehow you do something to a magnet that would produce an electric force on that charge? And people tried for a long time to do that, and Faraday was trying and wasn't able to do that. Brought very strong magnets next to a charge, and it wouldn't do anything next to a charged body. But then one day, by accident, when he had a wire and another magnet, and the magnet was brought up to see if any way you could induce a current in that wire, namely produce an electric force. And then he turned off the other magnet, and noticed when he turned off the other magnet, suddenly a current flowed in the first magnet. And he discovered something you've probably all learned, maybe, electromagnetic induction. The fact that, indeed, you can produce an electric force on a charge with a magnet, but the way you have to do it is you have to have a changing magnetic field. If you turn a magnet on or off, you'll produce a current in a nearby wire, because the magnetic field that turns on or off will produce an electric force on a charge that will cause the current to flow. And this was very important. But before he did this, Faraday, there was a great virtue of Faraday not having been trained in school. He said there was only one, he only ever written down one equation in his whole life. And therefore he didn't think mathematically. He thought pictorially. And people knew that charges had forces on other charges, and in fact you could write down the law of the force law between electric charges. Looks as the same as the force law of gravity. But for Faraday, he needed to have an intuitive picture, so he invented a concept which Newton before him had not. And this was the question. Newton, you may remember, he said, hypothesis non fingo, I frame no hypotheses. Newton was asked, how does the Earth know where the sun is to go around it? He said, I don't know, but it does. And so that was a real problem. And the same thing was with electric charges that Faraday was thinking about. How does an electric charge know another electric charge is there? But Faraday invented a concept that was useful to him. It was just a toy model for him. And it was this idea that around every charge was an electric field. He called it an electric field, and he said, well, I can picture it. Let me imagine the charge sitting there sets up through space these field lines, and the number of field lines is proportional to the charge. The more bigger the charge, the more field lines that are going out of it. And then, if I bring another charge nearby it, the reason it knows to respond is that it feels the field lines that are over here. This charge has set up a field throughout all space, so this charge here just interacts with the field here. In fact, you can make pictures of it. Two charges, each having their field lines. The field lines repel each other if they're the same, and the positive field lines go to a negative field line. So positive charges have field lines going out of them. Negative charges have field lines going into them. And you could draw these pictures, and what's amazing is you could say, well, if I place another charge down right here, I can determine what it's going to do just by looking at the field line. The charge is going to move in the direction of that field line. And what was amazing is this gave exactly, not just approximately, exactly the right answer just by pictures. You could do the answers by adding up electric fields and doing vector mathematics, which you could all do. But you didn't need to, and he didn't do it. The picture is what mattered to him. So he invented this mathematical crutch of these field lines, and just a mathematical nicety that was useful to him. And then he went on and did the experiments, which established, of course, everything today, because electromagnetic induction is the basis of motors and power and lights and everything you see. Changing magnetic fields producing electric fields producing currents. So when water goes over Niagara Falls in Canada and turns a turbine, which has a magnet on it, there's a magnet, and the turbine turns with wires on it. Those wires are moving in a magnetic field. They produce a current, and that's how you get power. Great. So it's kind of interesting, but so there was this new relationship between electricity and magnetism. And ultimately, that relationship was shown to mean, in fact, one person's electricity is another person's magnetism. Electricity and magnetism are not different things at all. They're really the same thing. It just depends on your point of view. For example, if you're at rest and that magnet is moving with respect to you, okay, you experience an electric force causing you to accelerate. But if you're moving along with that magnet, you'll see it as a magnetic force. So one person's you'd see this, both of you would see the same force, but one person's force that they call an electric force was another person's force that you call a magnetic force, and it depended upon your frame of reference. Okay, hold that in your head. The next major step was done by this guy. Who's this guy? Who? Maxwell, my real hero. He was the greatest theoretical physicist of the 19th century. He was dead by the time he was almost half my age. But nevertheless, in that time, he established the greatest unification perhaps in all of physics, but certainly the first great unification in all of physics, the theory of electromagnetism. He showed that there was a complete, if you wish, symmetry between electricity and magnetism, and he was able to put mathematical bones onto the framework that Faraday had established. And Maxwell showed in one of the best, most exciting calculations you can do. And I was going to do it for you here, but I don't want to take the fun out of your undergraduate physics teachers, because for me this is one of my favorite calculations you can do as an undergraduate. And for all I know, some of you already done it. But he could so he said, look, there's this big question. Well, forget the big question for the moment. He was able to show that there was this complete symmetry. If you think about it, the words I just gave you gave away the symmetry. So there's electricity and magnetism. A changing electric field produces a magnetic field. A changing magnetic field produces an electric field, with the fields just being these mathematical inventions. But then Maxwell asked himself the following question. By completing the mathematics of this, he realized what you could show was, okay, if that's really true, then there's a brand new phenomenon in nature. Because let's think what happens if I shake an electron back and forth. Shake an electron back and forth. Well, of course, it's a current. Okay, it's a changing electric field, so that produces a magnetic field. But if I constantly am changing the electric field, then it produces a changing magnetic field. One that grows and one that gets smaller. But that changing magnetic field will then produce a changing electric field, which then produces a changing magnetic field, which then produces a changing electric field. And he showed if you jiggle a charge, there'll be a disturbance in fields that move out. I probably have it here. He said if I jiggle a charge, I can imagine these fields moving out, because the changing electric field produces changing magnetic field, etc., etc., etc. And he said, okay, there's something really important here. How do I know? I can calculate the speed at which that field moves out. And that's the calculation that's so wonderful. You can try it at home tonight if you want, if you haven't done it, or you can wait till you're an undergraduate, a senior undergraduate probably. The way we can determine the strength of the force between two magnets is we measure it, and there's a force constant. So we measure the constant that tells you the strength of magnetism. And we measure a constant that measures the strength of the force between two charges. Those are two fundamental constants of nature. We measured them. We plug them in when you solve the equations. You plug in the strength of electricity and the strength of magnetism. What he was able to show is that, of course, the changing electric field and the changing magnetic fields produce each other in a way that depends upon the force. The strength of electricity and the strength of magnetism. So he was actually able to do the calculation when you jiggle a charge, how fast will that disturbance move out? And it depends on two fundamental constants, the strength of electricity and the strength of magnetism. If you just gave him those numbers, he could calculate what the disturbance would propagate at, and so could you. It's a beautiful calculation and relatively simple. And of course, what did he find out? He plugged in the numbers from the strength of electricity and the strength of magnetism, and he got a number like 3 times 10 to the 8th meters per second, which should be familiar to you. He got the speed of light. And what that told him, and what that showed, was now people knew what light was. Light was an electromagnetic wave. Because from this fundamental calculation, you can show if you shake a charge, you will produce a disturbance in these fields that propagates at the speed of light. And then Hertz was able to do the experiment to show that's exactly what happened. Shaking charge here would produce, light up a light bulb, as you may have seen in physics classes over there. But the important thing is that this was a fundamental calculation of the speed of light. And it also did something else. If you think about it, it was amazing. The fields that were invented by Faraday were just in his mind because he couldn't do math. Or he couldn't do algebra. He could do pictures. And they were just an invention of the human mind. But they are as real as anything. What Maxwell showed is those fields are not just a figment of your imagination. The fields themselves, you don't need the charges anymore. They produce disturbances in the field, and the disturbances in the field are so important that you can see me because of it. Okay? And therefore, these inventions of the mind were real. Electromagnetic fields were absolutely real. And they were different manifestations of the same thing. The first great unification in physics, two seemingly different forces, electricity and magnetism, were shown to be so integrally tied together they were really different manifestations of the same thing. And they were what tied them together was light. Light is the thing that tied together electricity and magnetism. And light was a manifestation of that. Okay, let's move on. Who's this guy? Everyone knows who that guy is. Okay, Albert Einstein. Now, I get letters every day from people who tell me that they have a new theory of everything, and want me to explain and want me to read it, which I don't do. And the standard line I get a lot is, you know, most of my friends think I'm crazy. And people I give this to think I'm crazy. But everyone thought Einstein was crazy. So they figure that if people thought Einstein was crazy and people thought they was crazy, they must be Einstein. There's some kind of transitive thing there. And, but more important, they say, I have shown that everything we now know is wrong. All of the science that we now know is wrong. My theory is right. And that's exactly, and just like Einstein, I'm revolutionizing physics. And then, of course, when you read that, if anyone ever says that to you, you can stop listening. Because that's exactly what Einstein didn't do. The biggest misunderstanding about Einstein and the revolution that is relativity is that he somehow did away with the physics that went before him. It was exactly the opposite. Why? Because if physics stands the test of experiment today, no matter what we learn about physics in the future, it'll always be true. So there's no way the physics of the future can ever say that the laws of electromagnetism are wrong because we've tested them in the laboratory. Whatever we learn at the extremes of scale, on the largest scales of the universe or the small scales of the universe, electromagnetism is still going to work because we've tested it. Now, what happens to that theory when you go to small scales or large scales may change, but on human scales it'll always remain the same. Okay. So what Einstein did, what the brilliance that Einstein did, was to take two things which were mutually inconsistent. Two results which were done by experiment, so they are both true, but they are both mutually inconsistent. And say, how can I live with that? The two results were the following. Galileo, as you all get subjected to in introductory physics class, showed that you can't tell whether you're moving or standing still as long as you're moving at a constant velocity. There's no difference. There's no experiment you can do in this room that'll tell us whether we're moving or standing still. In fact, lesser people than you think we're standing still, because we are. But of course, you know that we're really moving at 30 kilometers per second around the sun as I do this lecture. And between the time of the lecture, beginning the lecture and the end, we'll have traveled several thousand kilometers around the sun. So we're not standing still. But it doesn't matter, because we're relatively, because the curvature of the Earth's orbit is very small on that scale, we're moving in a straight line at constant velocity. Similarly, if you throw up a ball in an airplane and the windows are closed and there's no turbulence, or a train, you probably, those of you, if you're not in the States, trains may be better. I don't know if you've ever had this experience of being on a subway train system or a train station and sitting in your train and look at the train next to you and it starts to move relative to you. And for a moment, you don't know whether you're moving and they're moving until you start to feel the tracks. Okay? And it's true. There's no experiment you can perform, not a zilch, to say that you're moving or maybe the Earth is moving and you're standing still and the train next to you is going by. So that's Galileo. Basis of all of physics, that result. There's nothing more solid than that result. Well, there's maybe things just as solid, but that's one result. Then you come over here and you got Maxwell. And Maxwell said, I shake a charge and there will be a light ray traveling out at the speed of light which is determined by measuring the force of electricity and the force of magnetism. Those two things are mutually inconsistent. Most people didn't even realize they were, perhaps, but Einstein did. Now, what did Einstein do? Einstein didn't say, well, okay, I'm going to throw it all out. Okay, Maxwell's wrong or Galileo's wrong. One of them has to be wrong because they're inconsistent. Now, how are they inconsistent? Okay. Well, so here's Galileo. We're going along. And this example I first developed when my daughter was very young. So it involves projectile vomit. So she was just an infant at the time. And so I'm driving along in my car at, say, I'll use American units because they're easy for me at the moment. But we should never use miles, but I will. I'm driving along in a car at 30 miles per hour. Okay? My daughter's in the back seat, and she projectile vomits and hits me on the head. Now, the vomit goes from the back seat to the front seat at, say, 10 miles per hour. Okay? So, relative to me, the vomit hits me at 10 miles an hour. Now, what about someone on the ground? Someone on the ground sees my car going at 30 miles an hour, sees the vomit hit me, go from the back to the front at 10 miles per hour in the car, and therefore, how fast is the vomit going with respect to someone on the ground? 40. Good. Baby physics. Okay, great. But let's say my daughter is a 21st century child, and instead of a projectile vomit, she's playing with her laser beam. And she decides to point her laser beam at the back of my head. I almost blinded you there, Chris, but okay. Then what happens? Well, so I'm traveling at 30 miles per hour. She shoots the laser beam at my head, and the laser beam comes to me at the speed of light. Okay, so in relative to me, it's speed of light. But someone on the ground sees the laser beam in the car. Okay, and in the car, the laser beam therefore must be going at the speed of the car, 30 miles per hour, plus the speed of light, according to Galileo. Okay? But that's impossible, says Maxwell. Why? Because if that were the case, when this person saw the laser beam get turned on, they would measure the light ray as going at the speed of light plus 30 miles per hour. But remember, the speed of light is determined by two fundamental constants, the strength of electricity and the strength of magnetism. Therefore, if the person on the ground sees the speed of light to be different for that moving laser beam, then that person will measure electricity and magnetism to be different than the person in the car. But Galileo says no, because the person in the car must always measure the same laws of physics as the person on the ground. Okay? And therefore, you can't have your cake and eat it too. Galileo and Maxwell cannot be true at the same time. Because if they were, someone on the ground would measure the strength of electricity and the strength of magnetism to be different than someone in the car. That was the paradox. I'm always amazed it's never really explained that way. Because what we do to students, and this is one of the awful ways that science is usually taught in high school, is that you write down, and I'm glad I don't have a blackboard here, but someone writes down, the speed of light is constant for all observers. And it's like, it's like some religious dogma that you write down you're supposed to believe. Why? Because Einstein said so. Well, no one should believe anything because Einstein said so, or because I say so, or anyone says so. Einstein was driven to that, not because he said that would be a nice thing about nature, but he thought to himself, how can I make Galileo and Maxwell consistent? The only way they can be consistent, a lesser person would have said, well, there's no way. But what Einstein says, well, you know what? Maybe they can be consistent if they both measure the same speed. Me with respect to me in the front seat of the car, and that person on the ground with respect to them. Well, it doesn't sound too crazy, but of course it is crazy, because how can they be the same speed if one person is moving with respect to the other? Well, what Einstein said is, let's think about what speed is. Speed is distance traveled per unit of time. So maybe that person measures speed to be the same as this one because their distance and their time measurements change. So maybe nature adjusts itself so that the distance that I measure over here and the time I measure here is different than the distance and the time I measure here, because it's the only way to make those two things consistent. So in an incredible leap of courage, what he said is, instead of giving up all of the classical physics that went before him, he would say the two things that have been measured by experiment are both right, but if they're both right, space and time have to give. And the consequences, of course, of that are threefold. the three consequences of making the speed of light a universal constant, which is the fundamental principle of relativity. But it's not a principle based on revelation. It's a principle based on those two observational facts, are the following. Lengths contract. If the speed of light is going to be measured by all observers to be the same, regardless of their speed with respect to the light ray, then if I take this laser pointer and I'm moving very fast with respect to you and say it's 10 centimeters, okay? If I'm moving very fast with respect to you, with respect to me it's 10 centimeters, you will measure it to be 6 centimeters. Now, you might say, a big misconception is you'll say, well, that's just you measuring it to be 6 centimeters. No, it is 6 centimeters to you. It is, every experiment you could ever do on this would tell you it's 6 centimeters. Every experiment I would do on it would tell me it's 10 centimeters, and we're both right. Okay? The next one. Simultaneity changes. If lightning strikes here and lightning strikes there at exactly the same time, for me, and you're running with respect to me, you will say lightning struck in one place before the other place. And if you're running in that direction, you say lightning struck in one place before the other place. And we're all right. And Einstein said, well, that's the case because we can never be more than one place at a time. I know what happens. What's simultaneous for me right here, anyone else who's standing right beside me has got to see the same thing. But what happens at different distant points, I can only find out about by light. And what I infer from measuring that light will be that that event happened earlier than that event for me, or later and less late for you. And the last thing is time dilation, the very famous effect, the basis of science fiction movies, which is really true, that my wonderful Apple Watch will, if I'm traveling fast with respect to you, will be ticking more slowly. Something we measure every day in undergraduate physics laboratories around the world. If I'm moving with respect to you, my watch ticks more slowly than yours. Now, so those are the three consequences of relativity, but the next, well, I presented this picture for you because it should jog your mind. So what does this imply? Well, here we are in this cave. And in this cave, we measure that if you're standing still with respect to me, your ruler's 10 centimeters long. If you're moving with respect to me, your ruler's 6 centimeters long. So there's no such absolute thing as length, right? Wrong. Because we have the philosopher, mathematician, now natural scientist, and it was actually Einstein's math teacher, one of the few teachers that liked him, Hermann Minkowski, in 1908, who said, you know what, Einstein, your theory tells us that really we don't live in a three-dimensional universe. That henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. We live in something we now call a Minkowski space, where space and time are tied together. And we now understand that in that space, when I'm moving with respect to you, my ruler is rotated in a general kind of way. It's rotated in a four-dimensional space, and every time we look, we only see three-dimensional slices. So sometimes your space turns into my time, and sometimes my time turns into your space. Now, the rotation is a little more complicated in Minkowski space, but the idea is exactly the same. We have this quaint little notion that when we're looking out at this room, we're capturing everything at the same time, but we're not. When I look at you, the light from the people in the back of the room was emitted earlier than the light from the people in the front of the room. Every time I take a picture, I take a three-dimensional slice of a four-dimensional universe of 3 dimensions of space and 1 dimension of time. So when I take a picture, it's actually spread out in time. It's not in an instant. It's spread out in time because the people in the back of the room, the light from them had to leave earlier than the front. So when I take it, I'm taking a three-dimensional slice of a four-dimensional universe of space-time. And in fact, what you can show is when you consider that rotation in 4 dimensions, there is something that's absolute. In fact, the theory of relativities really should be called the theory of absolutes. Because space and time are relative, but space-time is absolute. There's a 4-dimensional length, a combination of delta x squared, minus delta t squared, the time difference between two measurements. That quantity is called the four-dimensional space-time, and that quantity is measured to be the same by all observers. So in a four-dimensional space, there really is something universal, space-time. And we were driven to this incredible realization that we live in a four-dimensional universe, just as Plato would have imagined that philosopher back 2,000 years ago would have discovered for people that they live in a three-dimensional universe when they saw length contract. And it all came from these quaint little experiments on jumping frogs that Faraday started to do. Led us to the second beautiful unification in physics, now in the 20th century. We had the unification of electricity and magnetism, but that very unification implied the unification of space and time. Okay, good. That was great. Then all hell broke loose. The universe was coming together pretty well. Four dimensions, electricity and magnetism, but then everything started to change. First of all, in the 1950s, we started building elementary particle accelerators and started smashing particles against each other. And what did we discover? Every time we ramped up the energy and smashed particles together, we produced more particles, new particles, and more energy, new particles. It looked like there were an infinite number of particles. Were there any fundamental particles? What was fundamental if every time you smashed one particle to another, you produced other particles? Were there anything truly fundamental particles? And a lot of people said, no, maybe it's kind of a Zen thing. Maybe every particle is made up of every other particle. It was stupid, but people were desperate. So, every time with cloud chambers, we ram particles together and see new tracks, and we discovered new particles, and it was all dependent on the energy. So it looked like there were an infinite number of elementary particles first. The next great discovery was that left doesn't equal right. One of the most common sense things we grow up to understand is that left and right are an anachronism. They're an invention that we use to tell ourselves how to go from somewhere to somewhere else. I have to remember which is left because I put my watch on that hand, so I can always remember which is left. But there's nothing fundamental about left or right. I mean, no one thinks that the laws of physics on the left side of the room are different than the laws of physics on the right side of the room. Nevertheless, the left side of the room is different than the right side of the room. The right side of the room has one person sitting in it over here. The left-hand side has maybe 20 people sitting. So there's no doubt, but that's an accident of the circumstances in this room. So we can tell left from right, and that's how we can get directions, because the building is on the left, it's not on the right. But that's an accident. No one thinks there's some fundamental difference between that and that. And there isn't. There isn't. In all the physics we could normally measure, in the way light behaves and gravity behaves and all the rest, left and right are just some convention. And it's an important convention, something you should think about. Again, I learned from Richard Feynman, and he gives a wonderful example somewhere. But try and think how you would give directions to someone on Mars who didn't know what left and right were. Okay, telling them how to get to their corner store when they landed. Okay, try and think about it. See if you could do it. Okay, have fun tonight with that. Anyway, two young guys discovered. I love these images, so I use them. We all know there's a difference between a left hand and right hand. But again, that's an accident. You can't turn your left hand into your right hand. It doesn't look the same when you do that, right? And this is a wonderful, this is a wonderful cave, not even a painting, done about 30,000 years ago, deep inside a cave in Germany. This is the kind of thing that I spend time thinking about. At 30,000 years ago, some adult took a child deep into a cave in Germany, put their hand against the wall, and sprayed paint over it. Why? Who the hell knows? Did they? But they did it. Thank goodness, and we now have that impression. But of course, if they did the other hand, it would be different. So those are different, but that's just an accident. But what was discovered by these two really young guys who weren't much older than you are now, a little bit, T.D. Lee and C.N. Yang, in the early 20s, was that in fact, if you looked not at the force between electrons or the force between planets, but there was a new force called the weak force. And I'll tell you about the weak force. The weak force is responsible for us being here. It's responsible for the nuclear reactions that power the sun. And it was only begun to be discovered in the 1930s, the nature of the weak force and what was responsible. They realized that, look, when you look at the weak force, there was a puzzle, and the puzzle could be solved if the weak force distinguished left from right. And the way you did it was, in fact, they proposed an experiment. If you have a neutron, and the neutron decays, as I'll talk to you about in a second, because the weak force decays into protons, electrons, and it turns out other stuff. And they showed that, look, if they were right, if you took a neutron and spinning, so neutrons spin like many elementary particles, and you put its spin axis here, and it decayed, protons and electrons would go out. But in fact, they wouldn't go out uniformly. You could determine an absolute left from, once you set the neutron up, then the decays would be, they wouldn't be the same number of protons going out in that direction as that direction. You distinguish left from right. That's what they proposed, and Madame Wu, an experimental physicist at Columbia, did the experiment. This was back in the days when you could make a proposal and then do an experiment at the weekend later, which she almost did. So in 1955, they proposed it, she did it, discovered that in fact that weak interaction is distinguished left from right, and in one of the only times it's actually happened, the Nobel Prize will was carried out correctly. The Nobel Prize was supposed to be for the greatest development in that field, physics or whatever, in that field in the last year. Okay? It never happens. I have many friends won the Nobel Prize for work they did 50 years earlier. Okay? But this time was so amazing. The notion that left and right were different was so crazy. These guys won the Nobel Prize in a year after they did it, when they still looked like they couldn't yet shave. Okay? Then we got this guy. Who's this guy? Richard Feynman, of course. I couldn't give a lecture without talking about Richard Feynman. Richard Feynman then showed that there was something even curiouser. It was first actually demonstrated by Dirac. But Feynman was the first one to give an argument for this. Okay? Feynman won the Nobel Prize for developing a quantum theory of electromagnetism. Electromagnetism, as Maxwell has shown, if you shake a charge, you emit light, and that's electromagnetism, and you can work out the interactions, and you can all wear the equations on a t-shirt that tell us everything you need to know about nature. Maxwell's 4 equations tell us how electromagnetism works, and that's true on the macroscopic level. But on the quantum level, it turns out that we now understand forces, the force between two electrons, as due to the exchange of virtual particles. That they're actually particles at the basis of light waves. Those particles are called photons, as you know. And so Feynman helped develop the mathematics that described the theory of electrons interacting with photons. And the way two electrons would know to be repelled by one another was not that this electron would set up a field necessarily, but the way we think about it from a quantum mechanical perspective is this electron is going along and it emits a virtual photon, namely a photon that you can't see, that basically, if you ever tried to measure, isn't there. And that virtual photon would be absorbed by another electron, and that was what would kick that electron away, so the two electrons would repel. Now, what are virtual particles? Well, virtual particles exist because of something called the Heisenberg uncertainty principle. The Heisenberg uncertainty principle says, as I like to say, the same thing as the White House and corporate America: if you can't see it, anything goes. And so the quantum mechanics tells us it's exactly that case. On scales smaller than you can measure, anything and everything happens, even things that seem classically impossible. And what the Heisenberg uncertainty principle says is that there are certain quantities that you can't measure exactly, certain combinations of quantities. One of them is energy and time. If I measure a system for a fixed amount of time, I can only measure its energy to a certain accuracy. To measure it more accurately, I have to measure it for a longer time. Well, that's the point. So when this electron emits a photon, it emits a photon with some energy. Well, that violates energy conservation, because you can't just have an electron sit there and suddenly emit a photon that has energy. Where did the energy come from? That's not possible, except quantum mechanics says, as long as you can't see it, it's fine. So the photon goes along and violates conservation of energy, but now you're measuring the system, and Therefore, if I measure it for a finite amount of time, I can measure the energy accuracy within a finite amount of energy, and that means the photon has to disappear before I can measure it that accurately. So if I emit a very energetic photon, that photon has to be absorbed really quickly, because it would violate the conservation of energy otherwise. And that's why electromagnetism is a long-range force. Because a photon is massless, to answer your question. And therefore, it can take up an arbitrarily small amount of energy. Therefore, when I have an electron over here, it can emit a photon that can travel all the way to Alpha Centauri, 4 light years away, before it gets absorbed, because in the process it can take an arbitrarily small amount of energy. And I'd never be able to measure the energy of this electron accurately enough over 4 light years, or 4 years, to know that that there was violation of energy. So that's why the only long-range forces in nature are the ones that have massless particles that are responsible for the exchange. And Feynman did a theory, the mathematics of this, and there were many problems in the mathematics, which I'll talk about, but he worked them out. But one of the things he showed is, okay, these are called Feynman diagrams, and he said, okay, well, I can think now of understanding interactions between particles. Particle A is moving along and then emits a photon, is absorbed by particle B, but of course, the interaction can happen the other direction. Particle B could emit the photon before and be received by particle A. There's no, and if you want to calculate the total interaction, you have to consider all possibilities. B emitting A to A emitting B, and all of those possibilities in between. But he said, okay, well here, let's just think, therefore, what can happen to an electron? Well, an electron is moving along, but remember the Heisenberg uncertainty principle. Electron's moving along less than the speed of light. Then, hey, I'm a quantum particle. I'm going to move along faster than the speed of light. Okay, nothing stops that. Nothing stops the electron from going faster than light. As long as it does it for such a short time, you can't see it. So you got electron, whoop, okay, good. That's allowed in quantum mechanics. But then there's a problem. Because relativity tells us that if you're moving faster than light in one frame, in another frame, you would be observed to be going backwards in time. So really, for another frame, if that would happen in another frame, then the electron would, moving forward in time, go backward in time for a little while, and go forward in time. That happens. But then let's think about what that really means. And Feynman said, well, imagine you're looking at he used the example of a bombardier during the war, looking down, and you see one road going along, and then you're traveling along here, you see one road going along, and then suddenly you see 3 roads, and then you suddenly see one road again. Well, what happened? You saw the road did a turn back. Okay? It was really one road doing that all along. But he said that's what, if you're thinking about measuring things, if this is really true, and you look at this in this frame, you start with one electron, but what does an electron that's going backwards in time look like? Well, it's a negative charge going backwards in time. But that is mathematically equivalent to a positive charge going forward in time. Right? If you're following the flow of charge, then a negative charge moving backward in time is the same as a positive charge moving forward in time. And therefore, he said, if you're going along, for the observer in the other frame, it would look like this. An electron's moving along, then at this point, out of nowhere, an electron is emitted, and suddenly a particle that looks exactly the same as an electron but has opposite charge is emitted. And then, at this point, this particle with opposite charge and this electron annihilate each other, and then you're left with one electron left over. So just by applying quantum mechanics and relativity together, we now know that suddenly empty space isn't empty, as I told you. Suddenly, not only does this imply that for every particle in nature, there must be a particle with equal and opposite charge and the same mass, the antiparticle. Antiparticles are required just by the combination of relativity and quantum mechanics. The two are inconsistent unless, which is what Dirac had first really shown, unless you allow for the existence of antiparticles. First, but then secondly, particles and antiparticle pairs can pop in and out of the vacuum, again, as long as the extra ones get rid of themselves in a timescale so short you can't measure it. But this says particles can pop in and out of existence, and So you not only have virtual particles, but you get virtual antiparticles. The world suddenly became a lot more complicated because you got now not an infinite number of particles, you got antiparticles. But you have antiparticles, and this is the reason they exist, ladies and gentlemen. And you now know why. You could have predicted it. If you thought about logically what I said to you in the first part of the lecture, now don't feel bad you didn't, because of course a lot of people could have predicted it and didn't for a long time. So this is why empty space has energy. And this is why inside protons, virtual particles are popping in and out of existence, and they can affect the properties of protons. And we now know that those virtual particles are there because we can measure them indirectly. Okay. Next. When I was in high school, I learned something amazing that I'm now going to tell you, and when you get as old as me, you can tell people your age and say that when I was in high school, someone told me this and it was amazing. I hope it's amazing to you. You are made up of mostly neutrons. There's one right there. Okay. More neutrons than protons, right, in the atoms in your body. But neutrons are radioactive. If I take this neutron here and hold it, it lives 10 minutes. That's the radioactive lifetime of a neutron. Now that should shock you, because you've been here for more than 10 minutes, as you've been painfully aware. But the neutron actually in 10 minutes will decay, as I told you, it decays into a proton, an electron, called in this picture a beta minus, and it turns out a weird new particle called a neutrino. My favorite particles in nature. In 10 minutes. So why are you still here if the particles that make you up should decay in 10 minutes? An amazing accident. The neutron, the difference between the neutron and proton mass is 1 part in 1,000. The neutron is just 1 part in 1,000 heavier than the proton. They're almost exactly the same mass. In fact, the mass of the neutron is almost exactly the sum of the mass of a proton plus an electron with a little bit of energy left over. That's why you're here. Because what happens? A free neutron decays, but then I let a neutron fall into a nucleus. What happens when it falls into a nucleus? It loses energy. That's what getting bound into a nucleus in. If you jump from the top row just to kill yourself because this lecture is driving you crazy and you fall down here, you'll lose energy in the process before you topple onto these poor people who feel that energy released on their head. Okay? So the neutron loses energy and it falls in the nucleus. But what did Einstein tell us? Einstein told us E equals mc squared. If the neutron loses energy when it falls in a nucleus, it loses mass. Now it's no longer heavy enough to decay into a proton plus electron plus a neutrino. So if you stick neutrons in nuclei, they're stable for that accidental reason that the neutron is just heavy enough to decay in the real world, but you put it inside a nucleus and it can't decay anymore. That's why you can build atomic nuclei. That's why stars can make atomic nuclei. That's why you're here, because that's how you can build up things from hydrogen to helium to carbon, nitrogen, oxygen, iron, and everything else that you just ate. Okay? A wonderful, amazing fact. And the force, as in fact Enrico Fermi, another one of my heroes, the last great physicist who was both an equally good experimentalist and theorist, doesn't happen anymore, because both fields have too much intellectual baggage. To be an experimentalist, you have to become an expert in all this stuff. It takes a lifetime. To be a theorist, you have to learn all this mathematical stuff that takes a lifetime. But Fermi was able to do both. And Fermi came up with a theory of that, with an idea of that called beta decay, which he presented, and it was a theory, and the neutron decays in his theory into proton and electron and neutrino, and that it gives the right answer, etc. Great. There's a problem with the theory, however, and it was recognized the following. Well, the weak force, neutrons decay, in fact, to go back here, at a point. At one point, suddenly you have a neutron, and then suddenly a proton, electron, and a neutrino come out at that point. So the weak force has a range that's incredibly short. You don't see a neutron over here and suddenly a proton, electron, and neutrino appear over here. Whatever causes that interaction to happen happens over a scale much smaller than the size of an atomic nucleus. Okay? And so people say, well, look, we got this great theory, quantum theory of electromagnetism that works. It's the best theory in nature, still the best theory in nature. Quantum electrodynamics. It allows you to predict to 11 decimal places or better fundamental quantities that you can measure. There's no other theory in the universe that we have that allows you to take fundamental quantities and predict answers to 11 or 12 decimal places and get the right answer. This is the best theory in nature. And it didn't take a rocket scientist, although it actually took about 20 years, for someone to say, well, look, you know, maybe if this theory works so well, I can maybe make a full good quantum theory, because Fermi's theory was just an approximation. I can make a quantum theory of the weak force by having the neutron, which turns out to be made of quarks, but that doesn't really matter, decay into an electron and a neutrino, but there'd be a particle exchange, because all forces in nature in the quantum world are due to particle exchange. But why would the weak force happen over the size of a nucleus? Well, I've given you the ammunition to give me the answer. Anyone? Okay, I'm not going to. What?
The carrier particle of the weak force's mass.
It has a big mass, that's right. Because I told you that if you carry a lot of energy, you have to disappear really quickly. A photon doesn't have to disappear very quickly because it's massless. That's why electromagnetism is long range. If you have a force carrier that's very massive, then whenever a virtual interaction occurs, it has to emit a very massive particle, a lot of violation of energy right there. It better disappear very quickly. Okay, so I can make a quantum theory of the weak force that looked the same as the electromagnetic force, but I have a heavy carrier. Great! The problem is nonsense ensues. What happens, I'll go back for a second. If you try and do the mathematics of this is the best theory in nature. It predicts everything all right. This predicts everything is infinite. That's a slight problem. And the problem is that this theory just doesn't make mathematical sense. Now, I want to just spend a little bit of time on infinities because they're so fascinating. Mathematicians love infinities. Physicists don't like infinities. This is Hilbert, the greatest mathematician of the end of the 19th century, early part of the 20th century. And he gave a wonderful example, which if you haven't heard, you'll hear. And if you've heard, you'll hear it again. Something called Hilbert's Hotel, to show how ridiculous infinity is. Let me give you an example. So, has anyone ever been to Las Vegas yet? Not yet. Oh, some of you have. Interesting. Okay. Well, there are these infinitely big hotels. So let's say you go to Las Vegas, an infinitely big hotel, and you go in, and let me just number the rooms of the hotel: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to infinity. And I go to the hotel. I get in at 1 in the morning, and I go in. I say, "Can I have a room?" And the innkeeper says, "That's full." And I go, "Okay, I'll go somewhere else." He goes, "No. We can fit you in." He goes, "How?" He said, "Well, it's very simple. I'll take a person from room number 1 and put them in room number 2 into room number 3, etc., 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 and now room number 1 is empty. I just move everyone over 1. Well, it's infinite. You're allowed to do that, right? That doesn't seem to bother you enough. Let's say you have a Catholic family that's infinitely big, and you and your children want to go into the room, in the hotel, and so you say, "I want to," and he says, "Full, but oh no, I can accommodate you. I just move the person from room number 1 into room number 2, the person from room number 2 into room number 4, room number 3 into room number 6, and now only the even-numbered rooms are occupied. But of course, there are an infinite number of odd integers, so we can fit your family." Okay, it begins to bother you. Let me give you an example. That's an artificial example. Let me give you another example of something that's actually relevant in physics. Let me ask you the following. What's this? And if you know the answer, don't tell me. You can only answer if you don't know the answer, okay? What's the sum of this series? The simple answer is infinity, so say it. Oh, very good. No! Okay? Yeah, see, I knew there'd be someone have to prove they knew the answer. Okay, the answer to this, first of all, we can write down that series in weird ways. We can call it the sum of, we can label it as a function, the Riemann zeta function, which is the sum from n equal 1 to infinity of n to the minus s. And if s is minus 1, then this is the sum of 1 to infinity of n, which happens to be this series. So the Riemann zeta function, we can define a generalized function where s is the exponent here, and if s is minus 1, it's this number. Then we can do something fancy and say, well, this s could be anything, not just an integer, but a real number, and maybe it could just be a complex number, and then I can rewrite the Riemann zeta function in some weird way, which we can do. And then we can do the answer. We can say, what is the sum of that series? What is the Riemann zeta function of s of minus 1? And the answer is, as the young man who had to shout it out, minus 1/12. Now this should bother you, because in fact, every number in this series is larger than 1/12, and every number is positive, but the sum is minus 1/12. Now you might say that's just a bit of mathematical wizardry, it's irrelevant. Well, maybe it is, but the interesting thing, and I won't tell you now because I was thinking of doing it, but I don't have time, is this sum is the reason why string theory requires extra dimensions. Turns out string theory, as it was originally defined, had a series that appears like this in it that gave nonsense. The series, it was times a number, which became infinite. And you would sum it up and get infinity unless the two other numbers were just set up so this series, which is minus 1/12, will cancel another series, which is plus 1/12. And those two numbers depended upon the dimension of space-time. And it turns out string theory requires, if you don't have weird other things, 26 dimensions of space-time. The reason string theory requires 26 dimensions of space-time is to cancel things because the sum of that series is minus 1/12. So if you think it's just mathematical shenanigans, maybe it is, but it's responsible for the reason that a lot of physicists began to think there were extra dimensions in nature because of this 1/12 had to be canceled. Okay, so maybe it is just mathematical shenanigans, but infinities are crazy, and the main point of this is if we want to come up with sensible physical results, we have to get rid of the infinities. Okay, how can we do that? Well, we're coming to the climax, which is good. Excellent. Those of you who live in cold climates, I've talked about this the other day, can experience the fact that when it suddenly gets cold, there are icicles on a window. And we can see the icicles on a window. If you've never seen them, they look like this. They're beautiful. Because we're standing outside the window, over here, looking at them. Pretty, aren't they? Okay. Now, if, however, you lived on one of those icicles, the world would be very different for you. If you lived on this particular icicle, that direction would be very different than all the other directions, wouldn't it? If on that icicle, your universe would say, there's a preferred direction in nature. Okay? Nature is such, if you only lived on that icicle, just like living in that cave, you only lived on that icicle, one direction would be different than all the other directions. Now that's an accident of your circumstances. We know that in the real world, doesn't matter, all the icicles pointing in the different directions are the same. But if you lived on one of them, it would pick one direction to be different. That's the phenomena of spontaneous symmetry breaking, we call it. What it means is the real world has a symmetry. It doesn't matter which direction you're pointing. But when you actually get a manifestation of nature, one direction is different than the other. For example, in this room, there's spontaneous symmetry breaking. That direction is different than that direction because I can go out the door in that direction. Can't go out that direction. But that doesn't mean it's just an accident of our circumstances. Now, Mr. Higgs and a few others pointed out the following. If we live in an icicle, if the universe is an icicle, and there's a background field that's invisible everywhere in the universe, but some particles interact with it differently than others, then the particles can initially be exactly the same, but end up looking different. It's like swimming in molasses. If you swim in a water, you can swim very fast. If you jump into a pool of molasses, you'll swim pretty slowly. Other things will happen too, but you'll swim pretty slowly. Now, you will feel heavier in that molasses. Another example, take a car. If you've ever had a flat tire and you want to push the car off the road so it doesn't get hit, you can push it until you get to the side of the road, which is mud, and then you can't push it anymore. the car suddenly becomes heavier. Well, it doesn't become heavier. There's just much more resistance when you try and push it through the mud, right? But it acts as if it's heavier. What Higgs and others said was, well, maybe there's this background field in nature, and some particles interact with it and other particles don't. And let's say photons don't interact with it, so they go along their rate like that. But let's say particles like the force carriers of the weak force interact with it, and it takes a while. You try to get through, and they act like they're heavier. So really, in a fundamental way, the particles are both massless. The weak particles that convey the weak force only act like they're massive because there's this background field. And if the weak particles that convey the weak force are really fundamentally massless at some fundamental physical scale, the mathematics of their theory is identical to the mathematics of electromagnetism, and all the infinities that disappear. And so, the third great unification of physics is to say, well, maybe the theory of the weak force, and it turns out there are three particles that convey the weak force, two charged ones and one neutral one, looks identical to the theory of quantum electrodynamics if you assume they're massless particles, and there's this weird field that makes these massive, that these interact with. Well, that's fine, but inventing a weird field is like religion. If it's invisible, it's like God, right? But in physics, if it's going to be relevant, you've got to be able to test it. Well, before we talk about that, let's go back to this. It was recognized that, look, if these things look the same, maybe they are the same. Maybe all of these are different manifestations of the same force, just like electricity and magnetism, which look different, are really, one person's electricity is another person's magnetism. Maybe at an underlying scale, these are all part of a unified theory where they're the same force, but because these have a different interaction strength with this background field, they end up looking different. So this one theory of two forces, the weak force and the electromagnetic force, is really a single theory called the electroweak theory. They're unified together, and it's an accident of nature that this begins to look different. And then it was up to these gentlemen to show that the mathematics worked out exactly right. Sheldon Glashow, who did it during his PhD thesis in 1961, Steve Weinberg, who did it in 1967, and Abdus Salam around the same time, said, look, maybe there's a unified theory of the electroweak force, the electric and weak forces, and they're all manifestations of the same thing. And the proof of it, because they were the first ones to put the meat on this picture, is that there'll be three particles here, and because they're the same force, they'll have very characteristic interactions with matter that you can measure. If you could just build an accelerator big enough to detect them, they'd have to be there. And I can tell you exactly what the mass is, because I can tell you how big the long-range force is. And they wrote down the mathematics of it, and in 1979, they won the Nobel Prize for producing the next great unification. We had electricity and magnetism. Now we have electromagnetism unified with the weak force. Now, there's a few things missing here. First of all, they wrote down the theory, but no one ever actually showed it worked mathematically, that the actual theory could get rid of all the infinities. These guys showed you get rid of all the infinities. This guy did it when he was a graduate student, Gerard Tuft and his thesis supervisor. And 20 years later, they won the Nobel Prize for actually, because no one, when Weinberg wrote down his theory in 1967, it had precisely 0 citations until 1971. No one cared about it until these guys proved the theory made mathematical sense, that the infinities really did go away if spontaneous symmetry breaking happened, and they won the Nobel Prize. Then you got these guys, and they showed, okay, you got the weak, you got the electromagnetic force, that there's one other force in nature, the strong force, the force that holds quarks together. And they showed that it was exactly the same type of mathematical theory could explain that phenomena, and in fact, that theory would predict something even weirder. That if you took two quarks and brought them together, the force between those quarks would get weaker the closer they got. completely non-intuitive, but quantum mechanics makes it happen. They called that asymptotic freedom. And they said if the same kind of mathematical theory called the gauge theory explains the strong force as explains the others, then because of its form, quarks, the force between quarks will get weaker the closer they get. And what do you know? In the 1980s, people began to measure things and discovered the force between quarks gets weaker. And in 2004, these guys won the Nobel Prize in Physics for that. And they're the ones who allowed that picture of what happens inside a proton to be actually calculated, because they have the theory called quantum chromodynamics. Quantum electrodynamics is a theory of electromagnetism. Quantum chromodynamics is a theory of the strong force. So now we have quantum theories of the 3 of the 4 forces in nature. Everything works out. All the infinities are gone. You've got theories that work completely and explain every phenomena we've ever observed in the laboratory. But there's a problem. The problem is, well, so this is what we got. One type of symmetry, every observation explained. And it led us, by the way, to, it made physicists, particle physicists, even more obnoxious than they were before, because we were convinced we're on the verge of understanding absolutely everything. But there was one little bit of, in this house of cards, that could make the whole thing fall down. It was based on this invisible field that no one could measure, or no one could measure up to that point. So the whole edifice could fall down if that field didn't exist. How do you find such a field? Very simple. You spank the vacuum. Sadomasochism in physics is everywhere. Because quantum mechanics tells us that for every field, there's a particle. And if I spank the vacuum hard enough at a specific point, meaning if I dump enough energy in the vacuum at a specific point, I can kick a real particle out. If there's a background Higgs field, if I put enough energy at a single point, I can kick a real particle out, and I'll produce a particle associated with that field. Now, the mathematics told us that particle was probably pretty heavy. So we built accelerators in the 1970s and 1980s, and then we were building an accelerator in the 1990s in the United States that would find it, we thought, but then Congress, in their infinite wisdom, said we can't afford it anymore. It's $5 billion. It's a lot of money. It's the amount of money of maybe the Iraq War, air conditioning in the Iraq War in a week. Okay? But then they thought it was a lot of money, so they canceled it. But then the Europeans built an accelerator and said, look, if this is empty space, the particles interact with it, giving the mass, we could turn the picture around and say, if we smash 2 particles together with enough energy, we can produce the particle that was responsible for the Higgs field. So let's build accelerators, in this case, build a machine that will accelerate protons around in one direction, and protons around in one direction and protons around another direction, and accelerate them to 99.9999% of the speed of light, so they get pretty heavy. And then smash them together, maybe with enough energy to produce the Higgs particle, producing the most complex machine that humans have ever built. This tunnel is 26 kilometers around. If you go to Geneva, the airport there, you won't see anything. You'll just see farmland because it's deep underground. It goes underneath the Jura Mountains here. And protons are accelerated 99.999% of the speed of light in that direction, 99.999% of the speed of light in that direction. They smash in a few places. And by the way, they go through this is the French-Swiss border. They cross the border maybe 10,000 times a second without passports. And it was hoped that they might produce the particle that was the manifestation of the Higgs field. And this is an observation. In July 4th, 2012, they discovered the reported discovery of 50 particles, more or less, that looked like a Higgs and sort of sounded like a Higgs. And if it walks like a duck and it quacks like a duck, maybe it's a duck. And in fact, how do you know? Well, remember, because the Higgs particle gives mass to other particles, the Higgs field, particles that are heavier must interact with it stronger than particles that are lighter. And therefore, if the Higgs particle is there and it's going to decay preferentially into heavier particles. It can interact more with them than light particles. So its interactions are prescribed by the standard model. And in fact, you can look at all the different kind of decays of this particle. We can predict what they would be in the standard model, and this was the early results, and they were all more, except for one, it was a 2 sigma away, but now is there, but 2 sigma differences happen all the time. Now we know we've discovered the Higgs particle. The standard model of particle physics is complete, starting with Plato, going through Faraday and Maxwell and Einstein and Feynman and all the rest. We took this incredible theoretical edifice of staring at a screen and realizing that what we see, the world we see, is just a manifestation of a deep underlying reality. And now we see that, if, in a sense, we are all living on an icicle. The reality that we see, our existence, our mass, is an accident of the fact that this background field exists. The fundamental particles in nature are all massless. And what makes our reality possible is that we're living in the tip of an iceberg. Now, we aren't done, and I'm almost out of time because I went slower than I thought I would. I like Impressionist painting, but the thing about Impressionist painting is it's great until you get really close to it, and then it looks crappy. And there was something interesting about the forces of nature. We measure the 3 non-gravitational forces of nature, the strong force, the weak force, and the electromagnetic force. They have different strengths as manifested at our scale. But one of the interesting things is, I told you the force between quarks gets weaker as you get closer together. That's equivalent in quantum mechanics to saying the force gets weaker as the energy scale at which you explore it gets bigger. And it turns out the strength of the other forces changed too. And it didn't take much smarts in 1974 or 5 to say, look, you know, although these two have already been unified by the single theory, but since they all come together, if you go to a really high energy scale or a really small distance scale, maybe they're all the same force. Maybe not just electricity and magnetism and the weak interaction unified, but maybe they're all unified in some grand unified field theory. And in fact, the problem is it's wrong. It doesn't work. We didn't know the exact strengths of the forces in 1974, but we measured them now, and we extrapolate them using the known laws of physics and the known particles in nature at some scale 16 orders of magnitude higher in energy than the mass of the proton, or 16 orders of magnitude smaller in scale than the size of the proton. They don't come together. But if there's a new symmetry of nature, supersymmetry, and if it's manifest at the scale of the Higgs, it predicts a whole bunch of new elementary particles in nature. They change the way those forces change. And in fact, if you put supersymmetry in, they all come together at a single point. A single point at a scale that's comparable, by the way, to exactly the scale where inflation might have occurred. And so it all is beginning to smell like it might be there. Except, if there are a lot of new particles at the electroweak scale, we should see them in the Large Hadron Collider, and we haven't. That's why we've turned it on again and increased the energy. It's now running, and it may tell us, if it discovers these particles, it'll tell us that we're on the right track to a unified theory that might predict a theory of inflation that ultimately might predict those extra dimensions that I talked about, the extra universes I talked about yesterday. Okay, they're not there. What if just the Higgs is measured and nothing else when the Large Hadron Collider turns on? Well, maybe there's something fundamentally wrong, or maybe they're just a little too heavy. Maybe we have to build another machine. But it's going to be a lot harder to build another machine because you can't go to Congress or to the European Union or whatever and say, guess what? Guess what? We turned it on and we didn't discover anything. Give us more money. Okay? It's hard. Maybe we'll continue. We waited 40 years, 50 years from the time of Higgs to the time we measured the particle. During that time, we came up with lots of theories, most of them wrong, probably. If we don't build another machine, we could be into another 50 years of sensory deprivation. We'll see what happens at the Large Hadron Collider. So, what I want to conclude with is that, in my opinion, the Large Hadron Collider is humanity at its best. The Large Hadron Collider and machines like it are the Gothic cathedrals of the 21st century. Gothic cathedrals were the most complex devices, buildings ever made in Gothic times. They celebrated the glory of God. They were beautiful, etc. They were built by thousands of artisans over centuries, working together to make a beautiful thing. The Large Hadron Collider has these amazing detectors that are gargantuan in size, built by thousands of physicists over decades, each of the physicists speaking dozens of languages, dozens of different religions, but they have to design machines that are accurate to the nearest millionth of an inch to make it work, and it works. It's an example of the fact that science, as we can see in this auditorium, is universal, is global. It doesn't matter whether you're Chinese or Japanese or from New Zealand or from the United States or from Singapore or wherever. We speak the same language, and it doesn't matter what our cultural backgrounds are or our language or our religion. We can work together to find a common reality. It's humanity at its best. There I am. That makes even a better picture of it. Let me give you an example of how hard this is, though, what they have to do. Every second, the Large Hadron Collider, every second, enough data is generated to fill more than 1,000 1-terabyte hard drives, more than the information in all the world's libraries. Every second that machine runs. We have to figure out ways to manipulate that kind of data. The machine itself is 26 kilometers around at a temperature of almost absolute zero with a vacuum better than the vacuum of space. There are fewer particles in that tunnel than there are if you go out into orbit among the Earth. The unbelievable requirements that were on this machine in order to make it work, make it the most complex thing that's ever been built, but it's built. But the last thing I want to end with then is if this whole theory is right, and it appears to be, we are just here by a cosmic accident. The fundamental universe doesn't look at all like the universe we see. And if the Higgs field in the early universe hadn't frozen in place,